Classical Physics of the 1890s by YKademy. In this video, we're going to talk about the main laws and theories of classical physics in this age. Scientists had made some important discoveries up to this time, and the best scientists of the day were highly recognized and rewarded. Public lectures were frequent. Basic research was recognized as helpful because of the applications which often followed. Scientists rightly felt that given enough time and resources, they could explain just about anything. They did recognize some difficult problems though. They didn't clearly understand the structure of matter, which was going under immense investigation. Nevertheless, on a macroscopic scale, they knew how to build efficient engines based on discovered laws of physics. Travel was frequent and most ideas traveled quickly among the centers of research. The classical ideas of physics include the conservation laws of energy, linear momentum, angular momentum, and charge. Conservation simply means that a quantity such as energy or mass is maintained at a constant overall total. We state these laws as conservation of energy. The total sum of energy in all its forms is conserved in all interactions. Conservation of linear momentum. In the absence of external force, linear momentum is conserved in all interactions. Conservation of angular momentum. In the absence of external torque, angular momentum is conserved in all interactions. And lastly, conservation of charge. Electric charge is conserved in all interactions. At that point in time, you may even add the law of conservation of mass to the ones above, although we know it's not valid today. These conservation laws are reflected in the laws of mechanics, electromagnetism, and thermodynamics. Electricity and magnetism were both separate subjects for hundreds of years, until they had been combined by the James Clerk Maxwell with his 4 equations. It is also important to note that optics had been shown by Maxwell, among others, to be a special case of electromagnetism. Waves which permeated both mechanics and optics were believed to be an important component of nature. Many natural phenomena could be explained by the wave motion using laws of physics. The classical ideas of physics also include mechanics. The laws of mechanics were developed over hundreds of years by many researchers. Important contributions were made by astronomers because of the great interest in the heavenly bodies. Galileo is one of the first great experimenters. His experiments and other observations laid the groundwork for the important discoveries to follow during the next 200 years. Isaac Newton was one of the greatest scientists of his time. His discoveries were in the fields of mathematics, astronomy, and physics. His discoveries include gravitation, optics, motion, and forces. We owe to Newton our present understanding of motion. He understood the relationships among position, displacement, velocity, and acceleration. He understood how motion was possible and that a body at rest was just a special case of a body having constant velocity. Newton's ideas were stated in the 3 laws that bear his name today. Newton's first law. An object in motion with a constant velocity will continue in motion unless acted upon by a net external force. A body at rest is just a special case of Newton's first law with zero velocity. This law is often called the law of inertia and can also be used to describe inertial reference frames. Newton's second law. The acceleration a of a body is proportional to the net external force F and inversely proportional to the mass m of the body. It is stated mathematically as F equals to ma. A more accurate statement relates force to the time rate of change of the linear momentum p. We can write this as force equals to the derivative p with respect to time. This takes into account mass flow and change in velocity. This has applications in both fluid mechanics and rocket propulsion. Newton's third law. The force exerted by body A on body B is equal and opposite to the force that body B exerts on body A. If the force on body B by body A is denoted by force A and force B, then Newton's third law is written as force A equals to negative force B. This law is often called the law of action and reaction. Not all forces obey the third law. These three laws can be used to define the concept of force, together with the concept of velocity, acceleration, linear momentum, rotation, angular velocity, angular acceleration, and even angular momentum. We can describe the complex motion of bodies. Classical ideas also include electromagnetism. The subject developed over a period of several hundred years. Important contributions were made by these great scientists: Coulomb, Oersted, Young, Ampere, Faraday, Henry, Maxwell, and Herschel. Maxwell showed that electricity and magnetism were connected and related by a change in the inertial frame of reference. His work also led to the understanding of electromagnetic radiation, of which light and optics are special cases for his four equations. Together with the Lorentz force law, they explain much of the electromagnetism. These main laws can be summarized as Gauss's law for electricity, Gauss's law for magnetism, Faraday's law, generalized Ampere's law, and Lorentz force law. These equations indicate that charges and currents create fields, and in turn, these fields can create other fields, both electric and magnetic. Classical physics includes thermodynamics. Thermodynamics deals with temperature T, heat Q, work W, and internal energy of systems U. The understanding of the concepts used in thermodynamics include pressure, volume, temperature, thermal equilibrium, heat, and entropy. Important contributions to thermodynamics were made by Benjamin Thomson, or Count Rumford, Carnot, Joule, Clausius, and Lord Kelvin. The primary results of thermodynamics can be described in two laws. The first law of thermodynamics: the change in internal energy delta U of a system is equal to the heat Q added minus the work W done by the system. This equation generalizes the conservation of energy, including heat. Second law of thermodynamics: it is not possible to convert heat completely into work without another change taking place. This implies that it is not possible to build a perfect engine or a perfect refrigerator, or even a perpetual motion machine. Heat does not spontaneously flow from a colder body to a hotter body without a change taking place. The second law forbids all of these from happening. The first law states the conservation of energy, but the second law says what kinds of energy processes cannot take place. For example, it is not possible to completely convert work into heat, but not vice versa, without again a change taking place. Two other laws of thermodynamics are sometimes expressed. One is called the zeroth law, and is useful in understanding temperature. It states that if two thermal systems are in thermodynamic equilibrium with the third system, then they are in equilibrium with each other. Simply, it says that if two systems are the same temperature as a third system, then they have the same temperature as each other. We can look at it as if A equals C and B equals C, then A equals B. The third law of thermodynamics expresses that it's not possible to achieve an absolute zero temperature. This wraps up the overview of the most important discoveries of classical physics until the 1890s. We will go more into depth into all these concepts in the coming videos. Hope you enjoyed, and if you did, don't forget to like, comment, and subscribe.